one of the biggest difficulties with unstructured data right now is that we have great tools for search and picking through, but that assumes you already know what you're looking for. And a lot of the time you don't know what you're looking for, especially if it's a brand new data set and you have no idea what's in it. So it's the tools that allow you to step back and see the big picture of the whole data set, or bring it into focus in a different way that's bringing in that sort of coherent whole information, rather than looking at the data through a straw of just search and return the most likely results to your search term that only answers the questions you already knew to ask.
How did the best machine learning practitioners get involved in the field? What challenges have they faced? What has helped them flourish? Let's ask them. Welcome to Learning from Machine Learning. I'm your host, Seth Levine. Hello and welcome to Learning from Machine Learning. On this episode, we have a very special guest, Leland McInnes. He's a researcher, a mathematician at the Tutte Institute for Mathematics and Computing, a Canadian research institute. He's the maintainer for many machine learning packages, including UMAP, HDBSCAN, PyNN Descent, DataMapPlot, which has created an ecosystem for unsupervised learning and has transformed the work that I'm doing. Leland, it is such a pleasure to have you here. Welcome to the show.
Thanks, it's great to be here.
So let's start off with this. What initially attracted you to the world of mathematics, computing, and research?
Well, to be honest, mathematics was something I grew up with. My father is a math professor, or was a math professor at University of Canterbury in New Zealand, where I grew up. By the time I was heading off to university, I wasn't sure if I was going to do math or not, but I ended up getting the opportunity to do math and physics, direct entry to second year. So I jumped in at that opportunity, and it turned out I liked the math more than the physics, and I had to quickly choose one or the other. Otherwise my course load got overloaded. So ended up in math, stayed in pure math for a while there, but I actually took a break from academia, went and worked in industry and with government for a couple years before heading back to do a PhD. So I have a little bit of experience with actually working with real data as opposed to pure theoretical math, but then I just stayed with the math for a long time after that. But working at the Tutte Institute, we have a bunch of different people working on slightly different problems, and I ended up leaning more into the data science machine learning questions, despite my, to be honest, pure math background.
Very cool. So what do you think, having that pure math theoretical background, how do you think that influenced your approach to some of these problems in the data science and machine learning world?
I guess I'm coming at them from a different perspective. So my background was in topology and algebra, so I tend to think of things in terms of algebraic structures and the geometry of things. So I'm always thinking in terms of the geometry of the data. I don't know if that's super novel, but it's, I think, a different take than I've encountered often chatting with people.
So I guess it gives you a unique view on how to think about data, how to explore data. And I guess if you think about the geometry of it, when we're doing something like unsupervised learning, you're trying to figure out the underlying structure of the data. So there's definitely something that goes hand in hand there. Do you want to talk about how you approach the unsupervised learning problem? Like when you get a new data set, what are you thinking about?
So unsupervised learning, that's definitely where I live, precisely for that question. It's like, well, what's the geometry? What's going on in this data set? Those are the questions that interest me personally, just trying to explore something new rather than the more supervised learning approach where, I've got a whole bunch of answers and I just want to reproduce them. I'm sure that's interesting, but it's less my field. I just want to understand data sets in general, and I don't think there are easy ways to do it for the vast majority of data that's out there now. So there's a lot of great exploratory data analysis methods for tabular data. If you've got a database or a spreadsheet with nicely formatted rows and columns, there's standard statistical approaches, faceted plotting. This is a well understood problem. But all the other data out there, which is to say the vast majority of data we collect, record, and store, is not that. It's free-form text, it's videos, it's audio files, it's system logs on computers, it's all kinds of things. And how do you explore that kind of data set? How do you understand what's going on in it? That's an interesting challenge. So that's kind of the sorts of problems I want to try and solve.
Yeah, and the amount of unstructured data is just continuing to increase, obviously exponentially. So yeah, there are different techniques and tools that you can use to take unstructured data and try to bring some structure to it. So I guess like each individual piece of data, and then also trying to understand how the data points, the interrelationships between those data points as well, and how you would group data, right? How you'd partition data, how you could explore the data, how you could visualize the data. And that's really where your libraries come in. I don't even know where the best place you would want to start with, in terms of clustering, dimensionality reduction, features. But what's the usual kind of pipeline, right? You have certain features for your data. Then usually there's too many features. You definitely can't visualize it because there's going to be more than 2, 3, maybe 4 if your dimensions. Then you're going to want to have it in a shape and form where you could do some clustering. Then you're going to want to visualize it. You're going to want to represent that data. So yeah, tell me a little bit about, the libraries that you have and how they address some of those problems.
Sure. So the first step is just getting the data into useful representation. And so that's turning this messy unstructured data into ideally something nice and mathematical, and vectors seem to be the world we live in now. So you need a way to vectorize the data. Now, there's a lot of neural embedding techniques, and they work super well, so I don't have too many solutions on that front. But if you have other kinds of data, we have a library called Vectorizers that tries to deal with some of the ways of getting other kinds of unstructured data into vector formats. So whether you're using fancy neural embedding techniques or something else, if you can get it to a vector, now you have something you can work with. Because now all the data lives in a space where hopefully distance between data points is a meaningful thing. So that means you have geometry of some kind and you want to explore that. So there's a few things you can do. You can try and pull out dense regions, groups, clusters, and you can try and visualize that data. Now, usually if you're using any modern vectorizing technique, it's going to give you very high dimensional data. It'll be anywhere from a few hundred to several thousand dimensions. That's really hard to work with. For starters, most clustering algorithms aren't actually built around that kind of data set. Most clustering algorithms, a lot of the assumptions that are actually quietly baked in behind the scenes assume that the data is pretty low dimensional, like anywhere from 2 to maybe 50, really. So your first problem is you have to manage to get the data to a state where you can cluster it reasonably, and then hopefully one of those clustering algorithms that are out there will do the job. So I started out by building clustering algorithms because that's what I was interested in, and then pivoted to how do I get the data to a state where I can cluster it. So I worked in dimension reduction after clustering, and that led to visualizable representations of the data, but then you actually have to make that work for people. And so DataMapPlot is my latest attempt there. So let's see, what are some of the libraries that go on there? HDBSCAN for clustering. So that's density-based clustering, but we want to be able to handle variable densities and do it as quickly as possible. UMAP is a method for dimension reduction and visualization. That'll get you either down to a clusterable number of dimensions, maybe 5 or 10, or down to 2 or 3 dimensions so you can visualize the data. There's also DataMapPlot, which the goal of that one is, you've produced a 2-dimensional representation of your data via UMAP, TS&E, it doesn't really matter. You can hand it to this program and it will make you nice, visually appealing static plots or interactive plots that you can explore and play with from there. So those are a few of the libraries.
Cool. So we'll start with HDBSCAN. So you started working on that over a decade ago at this point, right?
Yeah, about that.
What were you using for dimensionality reduction at the time?
I,
Different ones, or
I wasn't. I was working with lower dimensional data a
lower
decade
dimensional
ago.
data. So it was once the dimensions started going up, then you realized, okay, then you had to get
Yeah,
into
yeah, yeah. Then I had to pivot. Well, yeah. As you get to other data types, you suddenly realize, oh, this thing I was using is not working anymore. What's not working about it? So yeah.
Right. So with your implementation of HDBSCAN, I mean, there's so much to it. It's such a fabulous algorithm in and of itself. This extension of DBSCAN where you can kind of control some more of these things, and yours is fast also. How did you get it? I mean, in the most, I guess, lay terms, how did you get it to become a much faster algorithm?
Well, I mean, the algorithm was written by some other people who published great papers on it, but it was a slower algorithm. So what it came down to was I really read their paper and wrote a very basic implementation that was quite slow and was like, this does a better job of clustering than anything else. And then I just read some other papers, other random papers, and was like, oh, well, if I take this paper and just smush them together, then it'll go faster. And so it was really about the question of nearest neighbor search, because that was fundamental to what was going on internally inside HDBSCAN. So how do you make that faster? And there are some algorithms to do that. And it turns out that you can adapt them to work within HDBSCAN and make the whole thing flow together consistently. All the bits and pieces are slightly more messy and complicated than one would like. They're not the easiest of algorithms, so gluing them together took a little work, but really I'm just gluing together work by other people as far as I'm concerned.
Yeah, that's sometimes the most, like, that's sometimes when the breakthroughs happen, when you take the best pieces of them, or you can apply something from some other type of technique to the work that you're doing. What was the speed up? It was like what, n squared to n log n or something, n log n.
Yeah.
So you had to be looking up everything for every point before, and then using minimum spanning trees, or yeah.
So the problem is that it wanted to compare every pair of points. That gives
Right.
you your n squared, but you can use space trees, space partitioning trees, to cut that down to n log n. Although that doesn't work in high dimensions, it turns out, because space trees don't work very well in high dimensions. But that's
Right.
okay, because you just need to get down to low enough dimensions to make it work first.
Yeah, so I guess that then brings us to UMAP, the really a breakthrough. I know that a major breakthrough in dimensionality reduction, being able to capture both, local and global structure of the data. But yeah, so you've had this problem where now you're dealing with data that had, I guess, a higher number of features, and you had to reduce the data. So yeah, tell me about your thought process in creating something like UMAP.
Well, I mean, I think the real breakthrough actually was TSNE.
Okay.
That came out in 2009.
That was Hinton.
Yeah. Lawrence van der Matten and Hinton. And I think that was a real breakthrough, because it really demonstrated the possibility of these kinds of algorithms in general. Nothing else in dimension reduction or manifold learning up until then had really been as effective, especially for like visualization. So getting down to really small numbers of dimensions and having still good representations that capture a bunch of useful information. So I think that's where it started. So I was very impressed with how effective that approach was. And so I just wanted to build a method that would work with the math and theory that I was familiar with. So for me, that was very much sort of, as I said, geometry of the data, algebraic topology was what I knew. So I was trying to build a theoretical basis for an algorithm out of that. Then it's just a matter of slotting various pieces together. Again, like I was a bit of a magpie and grabbed different papers from all over the place. So, there was a paper by David Spivak on fuzzy simplicial sets, which I read and realized. So I actually read it because I was interested in it for HDBSCAN, and it it had a lot of application there in some ways, because again, HDBSCAN you can view from an algebraic topology lens or topological data analysis lens. But it really just opened my eyes to the possibilities of what one could do and how one could interpret things. And so just grabbing random bits and pieces of interesting math and algorithms and gluing them all together.
Very cool. I've used, well, yeah, I mean, all of your libraries a lot. But UMAP in particular, you really see how using different parameters, you can get very, like, wildly different results. Sometimes it's hard to know and like evaluate, you know, if you're like, how do you know if you're reducing dimensions correctly, right? Like, do you have any sense of that, or?
I have some sense, but so actually this is a challenging problem, and I think the answer is that you don't, because it depends on what you're trying to do with it. What is it that you're trying to represent in low dimensions? I think this is a problem also for clustering that I find is a bit of an issue, is people expect the clustering algorithm to produce like the true clusters, but there aren't any singular true clusters. It depends on what kind of things you want to get out.
Right.
And so expecting there to be some magical true answer and, you know, these other algorithms are approximating, or how good do they compare to the true clusters, is like, there isn't a single right answer. And
Right.
So, you know, that's the disappointing thing with unsupervised learning. Supervised learning, you've got all these metrics and you can measure how well you're doing. Unsupervised learning, it's kind of just like stare at it and go like, well, this is doing what I need. That's good
Right.
enough. Which
Yeah.
is unsatisfying in some ways, but at the same time, if it's doing what you want, isn't that good enough?
Yes. Yeah, it depends so much on what the use case is. Clustering is such an art. I think of it as equal art to science. How many clusters should there be? Just understanding that, what should the structure of them be, like, you know, having them in hierarchical nature, understanding what the group should be, understanding what point that group should belong to, you know, all of those things, depending on what the use case is going to be. What are you going to use it for? Is this to set you up for some supervised learning later? Is this just some exploratory data analysis? Is just to figure out, you know, some idea of how you could group or think about your data set. Something that you've said that I really liked is that while it might not give you the answers, it helps you ask better questions of your data. A lot of these tools.
Yeah, and that's very much what I'm interested in. I think one of the biggest difficulties with unstructured data right now is that we have great tools for search and picking through, but that assumes you already know what you're looking for.
Right.
And a lot of the time you don't know what you're looking for, especially if it's a brand new data set and you have no idea what's in it. So it's the tools that allow you to step back and see the big picture of the whole data set, or bring it into focus in a different way that's bringing in that sort of coherent whole information, rather than, you know, looking at the data through a straw of just search and return the most likely results to your search term that only answers the questions you already knew to ask.
Right. So going back into UMAP, you were inspired by TSNE, but so why was there a need for another dimensionality reduction algorithm?
It's a good question. I mean, TSNE was at the time on the slower side, and it had a tendency to kind of smush all the clusters kind of together. It separated them into clumps, but all the clumps were just wherever they landed. And I was interested in something that could get a little bit more of that non-local structure, some representation of how the clumps relate to each other, and also just a lot faster, and with a theory basis that I understood because I wanted to extend it in various ways. So one of them was semi-supervised and supervised versions of dimension reduction, but it's provided a framework for me that I can hang a lot of different adjustments to it too, which is why I don't know if you've looked at the input hyperparameter set for UMAP, but it's kind of excessively large. It's because I just kept seeing good ideas and going like, oh, I can add an option for that.
Yeah. We could talk about a couple of them. I mean, the ones that I think are my go-tos are obviously number of neighbors, min distance, number of components, depending on the visualization. Those are the three I play with the most, but I've dabbled in some other ones. Any other good ones that you wanna talk about?
So one actually is output metric. That's kind of fun. There's a metric parameter where you determine how you're measuring distance in between data points, but you can determine how you want to measure distance between data points in the output space, in the embedding space. So if you know that your data has periodic structure, it loops around, you can embed onto a torus, not the plane, or onto a sphere. Or one of the interesting options is you can embed not as points but as Gaussians with a covariance structure, and measure distance between Gaussians. So then you get an embedding where points have some uncertainty about where they're going to land.
Very interesting. Yeah. It's sort of going back to like what your use case is for what you're doing. If you understand what the use case is, then you can incorporate that into the parameter. Very cool. In terms of UMAP and creating a library like this, so you were kind of creating it to, scratch your itch, right? To solve your problem. But there's so many of the visualizations of data are using UMAP now. What are some of like the most unexpected uses of UMAP that you've seen?
So in 2020, I was very surprised to see it coming up in COVID research repeatedly, which, as a mathematician, that was not something that I felt I would ever be able to contribute to.
Right.
And yet at the same time, like that was at the start of the pandemic when, everything was panic stations. It was really interesting to see that I had managed to do something that helped some people somehow on solving this problem. That was inspiring.
Yeah.
It gets used in art actually a bunch. The pictures behind me are by an artist, Refik Anadol, who uses UMAP among many other machine learning tools to help develop art. There are a bunch of other artists I've been in touch with who also make use of it in various ways, and that's not a use case that I ever had in mind.
Right. Yeah. Well, the outputs that you can get are quite beautiful. The interesting thing from my perspective is, so I was doing topic modeling, I guess before UMAP. I was doing it when LDA, LSA, NMF, were just the state of topic modeling at the time. And now I've seen how your libraries have transformed this whole topic modeling space. A highly used library like BERT topic, the default parameters for dimensionality reduction, library that you're the maintainer and one of the creators of is UMAP, and the default clustering algorithm is HDBSCAN. Same thing for you. So I have witnessed your work transforming the work that I do. Every data set that I take, the first thing I do is run it through some pipeline that involves your libraries. And now, as of late, I've been using DataMapPlot, which is such a cool visualization library. There's so many cool things that are happening because when you try to you never know exactly what you're going to get, right? When you get an output, you could have 40 clusters, you could have 400 clusters, you could have depending on what your data set is. And the nice thing is you've created something that by default tries to give you a really nice output that you can just kind of just take it and you can read. Sometimes you have to do some minor tweaks, but a lot of the things are done in the back end for you. So you don't need to worry about a lot of the spacing and a lot of that stuff. What was what was the motivation there? You just wanted a way to visualize some of these outputs?
I think The real motivation was for some internal use cases. I've seen people using this, and they were giving presentations at the end of a workshop or something like that, and they'd put up some nice UMAP plots, and they don't have a lot of time. It's a short workshop, and then they want to give a presentation on the work they did, so they just plot however they can. And I would look at it and be like, if I had the time, I could get in there and I could, tweak a bunch of things about that plot and make it look a whole lot better. And I saw that happen often enough that I realized it's not fair that, like, I have the time to sit down and tweak all the parameters on the plot, but these other people, they don't have that experience of having done a lot of these kinds of plots, and they don't have the time to fiddle with Matplotlib or something like that for, a couple days to make the plot look just so. I should take all the stuff that I've learned and just try and shove it into a library that allows them to get a pretty looking plot that does all the things that I would want to tweak for them out of the box, and then hopefully give them enough knobs that they can make it look like what they want at the end of the day as well.
Yeah. It's such a great tool. I mean, in so much of the data science work that we do, like, there's the technical, the heavy aspects, there's the coding, there's the understanding of the data, there's the data engineering, but almost equally, you have to be able to share your results, right? And you have to be able to, like, kind of let other people in from all different levels, executive level, different technical level, anyone. And those types of visualizations, that's what I get most excited about, is that when you show someone like that, anyone can kind of relate and anyone can quickly understand. So just, like the power of visualizations, if you wanted to, like, dial in on that, how a visualization and the ability to kind of share your work and get other people involved in it, how that kind of helps you with your work.
Seeing your data is just such a wonderful experience, because we're visual creatures. Our vision is our primary means of getting input into our brains. If you can turn data that's this giant mess into something that somebody can see, that's an enlightening experience. And I've had, plenty of cases where I've worked with, domain expert on data set that they care about, that I realize I know nothing about. But we can work through, get it to a plot, stick it in front of them, and their first question is almost always, well, what's that and why is it there? Because there's something new in the data that they didn't realize was there, and then we have to dig in to those questions. And so that's where I guess also the interactive plotting really starts to provide a lot more value, because just seeing the plot is good, but now I want to answer the questions. So how do I do that bit next?
Yeah, that's a good point that you brought up, because, like, at first I was just thinking about, like, oh, you're exploring the data, but why are you exploring the data, right? Like, yes, you want to figure out good groups, but yeah, another thing that I always find whenever I create that output, you always figure out where those outliers are, or like those weird artifacts of the data that somehow got in there, and then you can kind of figure out a strategy of how to deal with that. And then what I'll do is I'll kind of just, like, do like a loop of that. Right? Like, I use clustering to figure out what data points maybe I should pull out, and then I find UMAP works better. Then I find, like, HDBSCAN works better, and then I just kind of, like, keep doing this iterative process, which ends up giving you some really nice results. It's amazing, like, how outliers can affect like everything. But that's why HDBSCAN handles noise. That's one of the things that makes that a very robust algorithm. Yeah, your work has just got. I'm happy that we're talking, because I remember I posted something. I used one of your visualizations in one of my projects, and I was looking forward to chatting with you. And then we bumped into each other in New York when you were on that panel with Hugging Face, because the work that you're doing, it makes the work for so many other people so much easier. So much easier. So many of the things are abstracted away, where you can just kind of focus on your data sets, focus on understanding your data better, focus on asking better questions of your data. And I think it's probably because you went in, right, and you weren't allowing it to be a black box, right? In one of the times that you spoke, You mentioned something about like decomposing these black boxes, and then that kind of sets you up, and you can understand how these things interact with each other. Can you talk to that?
Yeah, I mean, so this is a thing that I definitely see. And so you mentioned Bertopic, and Martin Grutendorst, who wrote that, has done a fabulous job with that of exposing the innards as Lego bricks that you
Right.
can swap in. So yeah, the defaults are UMAP and HDBSCAN, but you can use an SVD and then k-means if you want, or you can swap all the different components apart. And so seeing it as this composable piece of Lego bricks, I think is really valuable. But the same applies to even the innards of the other algorithms themselves. So personally, I see HDBSCAN as a pile of Lego bricks. There are a bunch of different things. So there's a density estimation step, there's a connectivity related step, there's a building a tree of clusters step, and then there's a cluster extraction step. And these are all, like, there are different algorithms for doing each of those things. HDBSCAN packages together a default set, but you can easily swap out each of those parts with something new. It's just a pile of Lego bricks. And the same with UMAP. There's constructing a representation of the high dimensional data in some sort of graph-based way. If you want to think in terms of algebraic topology, it's a simplicial set. But there's lots of different ways of doing that. You could swap out that component. There's how you're going to optimize a low-dimensional representation. Again, this is just components and pieces. If you look at something like LDA, a lot of that you mentioned as earlier topic modeling, one way of looking at that is, this plate model in the probabilistic view, but you can also just view it as a matrix factorization algorithm and decompose it into the parts of how matrix factorization works and give yourself, if not an understanding of everything there is to know about it, an understanding of the pieces and how they fit together in a way that would allow you to adapt it to different problems if you wanted to do that. So, it works with categorical data because you're looking at a distribution of words, and the prior for that is a Dirichlet distribution. But if you had count data that was much more Poisson distributed, well, then you need a prior for the Poisson. There's gamma distributions for that. You could build an LDA-like algorithm pretty easily that would work for an entirely different data type if that's what you want to do, if you have broken it down into the pieces like that. I think more time spent understanding what the actual pieces of these algorithms are is pretty valuable if you ever want to adapt them or use them for something else.
Right. That makes a lot of sense. Yeah, if you don't just say, "Oh, this is a black box. I'm abstracted away. The only thing I have control over just, these parameters." Well, you'll never really be able to fully grasp what's taking place. You won't be able to really build on top of the work in a way. So you have to decompose those things. That's probably my guess on why you have PyNN Descent, I would say.
Yep. So, I mean, you talked about taking pieces to make tasks easier for other people. PyNN Descent is an example of me taking a piece that makes work easier for me. Because nearest neighbor search, I mentioned HDBSCAN needs to make use of some of those sorts of things. This is also comes up a lot in UMAP. It comes up a lot in a lot of other places. I needed a thing that would do that in the ways that I needed it done. So, again, I'm borrowing algorithms from other people. There was a great paper on an algorithm called nearest neighbor descent that builds approximate k-nearest neighbor graphs very efficiently. There's a bunch of, again, that decomposes into chunks, and you can pull apart the pieces, swap in some other pieces, change a few other pieces, and that's what I did with PyNN Descent to get the implementation that I have that solves the problems I have. So I wanted things like work with a lot of different metrics. A lot of approximate nearest neighbor search will do Euclidean and cosine, and that's it. I wanted to be able to do anything. And I needed to be able to work with sparse data structures as well. So again, does that out of the box. These are, problems that I needed solved, and it was best to just package it up, and now I get to reuse it all the time. So I have a new clustering library called Evoke for embedding vector-oriented clustering, and it steals a whole bunch of stuff from PyNN Descent because it saves a lot of trouble to just reuse all of that work. Packaging them up so they can be reused, but at the same time being able to decompose them back again into the parts that you need.
So yeah, you've basically created a whole ecosystem of all of these parts that you can fit together to approach many different problems, but specifically like unsupervised learning in a very powerful way. In terms of the future of some of this work, or maybe one of the challenges in unsupervised learning or topic modeling in particular is something like trying to find new topics over time, right? Trying to incorporate the temporal feature. Have you thought about that? Have you been thinking about that at all?
Yeah, so temporal topic modeling is definitely something I've been giving a bit of thought to, and how best to handle that. There are algorithms from topological data analysis, an algorithm called Mapper that's based on Morse theory that actually lends itself to these kinds of problems pretty well. And I actually just recently had the opportunity to work with a co-op student who was visiting the Institute. He's now off doing his PhD at Waterloo. He worked on a paper on an extension of Mapper that would be pretty much ideal to solve this kind of problem specifically for the kinds of things you get from topic modeling over time. So that's hopefully that's on archive now, and if people want to go and read a highly theoretical paper, I'd recommend checking out that. I don't have the link on me at the moment, but
I can add it.
These are fun and challenging problems. So adjusting over time is a big challenge. So again, another thing that would be great would be to have a UMAP embedding that can evolve over time as new data comes in.
Yeah.
Right now, if you rerun UMAP, it gives you qualitatively pretty similar results, but it's invariant. The optimization problem's invariant under rotation and flipping. So at the very least, it could, flip things around. And if you just use the transform method as it exists now, that is based on the data that we've already seen. It's just going to fit new data in as best it can given this training set. So if a new cluster of data actually shows up, it's just going to squeeze it in amongst all the other data that's there. So there is some ongoing work to try and make a version of UMAP that would allow you to evolve in this way.
So like sort of adapt to the new data that comes in. So if you get like, let's say you're looking at like a month of data, then like another week of data comes in, instead of just trying to force that week into the last month, it would be adapting and changing. So if a new cluster came up, you could see that new cluster. Or
Yep, a new cluster would form, and the rest of the data would have to like move to fit around it, and so on. Yeah, that's very much the goal, and I think that's definitely possible. So there's some great work being done by some other people on that I'm desperately trying to follow and keep up with, and will happily merge into UMAP main as soon as they get it in the state that they're happy with.
Very exciting. Cool. So we talked a lot about unsupervised learning. I want to zoom out a little bit, and I'm going to ask the question around the hype of AI and machine learning. There's all of these promises are being made, and coming from somebody who, is creating these algorithms, seeing the things that we can do, maybe seeing some of the limitations. I'm curious what your view is on the gap between the hype and the reality that you see.
Let's start with the reality. There's a lot of value in a lot of the stuff out there. It has enabled all sorts of things that are really just incredibly powerful and useful. But the hype is something else again. Like I'm not a fan of the amount of hype around a lot of these things. I mean, for me personally as a user, a lot of the value in the generative large language models is just as a natural language interface, right? Like, retrieval augmented generation is the thing, but really that's old school information retrieval. Does a whole lot of hard work.
Yeah.
and then you hand that to the LLM, which does the interfacing to the user of taking the question in natural language and then taking those information retrieved results and turning it into a nice natural language answer to the question. Now, there's a lot to be said for the value of providing a natural language interface to computers for users. So there's the value. That's a huge value proposition, but that's not what most of the hype about them is about.
Right.
And at the same time, I think a lot of the embedding approaches where you vectorize text, images, video, whatever, and just turn it into vectors, a lot of people seem to view that as a thing that you can then put in your retrieval augmented generation system. But it's so much more valuable than that, and there's so much more you can do with that. I think there's untapped value there still in all the various things. Topic modeling is one example, but you could easily convert that to topic modeling for images. I think BurTopic already supports a basic version of that.
Yeah.
But you could turn that into all kinds of things very easily.
Yeah. One cool injection of generative, or the complement of generative to topic modeling, was one of the toughest parts was you get your clusters in the end, and you just have to kind of figure out what the name is and how to define what that topic is, and things like that. So that has been for me, an exciting use case of generative. Maybe not everyone would find that exciting, but if you know the pain of trying to name all of your clusters,
yes,
and if you can get anything to help you do it, that for me felt like a very good and valuable use case for generative. Like, here, take, with these keywords and take with these example documents, and now give me a good 3-word or less name for this cluster. It allows you try to understand your data quickly or get a good sense of your data quickly, create potential classes. That's something that I've found. But yeah, in terms of the hype of all of this couldn't be higher. It's supposed to solve all of our problems. RAG systems in general, the idea, I'll just vectorize everything and I'll just find the most relevant documents. Then you haven't really used cosine similarity, because you don't really or you need
information retrieval is really hard.
It's hard, and people have been working on it for a long time, and there's a reason why there's so many different algorithms. There's a reason why there's whole businesses around it, and you have to take into account so many things. Obviously, semantic patterns, lexical patterns, just incorporating metadata. I've found some. You could call them RAG systems, but just being able to retrieve the necessary documents just by kind of using other types of filtering, that can give you very, very good results. It is exciting to see what will happen, but I think that there's a lot of hype and new terminology being used for things that have been worked on for a long time. Yeah, for a long time. What do you see as a question that you believe remains unanswered currently in either machine learning or some of the work that you're doing?
So I think there's a whole lot of scope for work to be done still in unsupervised learning. That's hugely biased because that's the field I work in, but I look at the state of things and I'm like, this could all be so much better. It's not like I have the answers for how to make it better, but I can definitely see lots of room and directions for improvement. Even simple things like we have these sentence embedding models like SBERT, and they're fantastic, but do you need the full power of a giant transformer-based neural network to make that work? Because I'm a fan of what's the simplest possible thing you can do that still does a good enough job.
Yeah.
And I'd be really interested to know if you can produce sentence embeddings 98% as good as the transformer model with something that's just way simpler and easier to understand, because the internal workings of what that pre-trained model has learned, that's harder to pick apart. But if you've got so that's a black box that's harder to decompose.
Yeah, for sure.
Into pieces. I'd love a more decomposable version of, say, sentence embedding or vectorization or any of these sorts of things.
Yeah, so some of the interpretability and understanding of those embedding models, There's a lot of very interesting work. Tom Arson is doing an incredible job with sentence transformers and the ability to create custom embeddings and things like that. That's something that I'm very excited about. But yeah, like, I mean, to go into some of the things that we were doing, like, yeah, you create these embeddings. They're 512 dimensions, 768, 1024. Like, they're huge sometimes. And it's like, well, do you really need it to be that big? Then you have to go through some sort of dimensionality reduction. I wonder if there's some combination of embeddings that could feed right into a clustering algorithm. That's something that I think would be cool.
Yep, yeah. But now you need to decompose the parts and glue them together slightly differently. For like, if you have a specific task, there's definitely things you could do. How does that work? I don't know, but I think there'd be great answers if you could figure it out.
Yeah. Well, there has to be some things that we don't have the answers to, so there's a reason to come and continue thinking and working on all this stuff. There's so many exciting things. All right, to zoom even further out, I'll ask an advice question. What advice would you give to someone that's just starting out in the field of either research, data science, machine learning?
So specifically for data science and machine learning, my advice is don't follow the hype in the same direction that everyone else is going, because you're not going to make a dent in the field that everyone is already working on. Go do whatever is interesting to you that isn't necessarily the hype thing, and be good at something that you're good at, and that's probably going to be good enough. The time will come when whatever you're working on will come around. So, and the other thing is that I think interdisciplinary spaces are where a lot of value comes. That doesn't mean you need to split yourself between like two wildly different subjects, but if you can find some time to stretch into subject areas that people aren't otherwise necessarily working on, that can make a big difference. I mean, I kept talking about being like a magpie and just grabbing different random bits and pieces to stick together, and that's because I touched on a few different fields. So, you know, a bunch of pure math, but some machine learning things, algorithmic things, and just being able to have enough of a stretch to grab things from different fields that other people aren't putting together. That's often what you need to create something new.
Yeah, I have to agree. And then just like a small extension of that, I guess the interdisciplinary part to it, I always found, like, when I was doing research, when I was, in my engineering program, you could be very insulated sometimes around people who are very like-minded and who approach the problems in the same way. So sometimes, like, being exposed to other people that are just look at the world in a different way or think of the problem in a different way. Are there any people, either in your work or in the field, that you found that have kind of like opened up the way that you think about things?
There are many people. Let me see if I can think of a few that just spring to mind. So Matt Rocklin, who built Dask and runs Coiled. I don't know if you've ever had the opportunity to interact with Matt or watch him interacting with other people, but he is amazing at going and listening to people about whatever their problem is. And that is inspiring, because that's how you actually find out what you need to build. Not necessarily sitting down yourself and coming up with the whatever you think is cool. Work out what the problems that your potential users are actually having actually are, and listen to them. So, and that is something Matt is amazing at that. Who else? Lorena Barba has done amazing work on reproducibility and also just education. So thinking about how to explain things well, especially with like interactive tooling or anything like that. She's done a fabulous job about just computational thinking in general. Vincent Warmerdam is awesome, because he always wants to build the simplest thing that still works, and that is very much something that I definitely believe in. And he's just so great at always putting those together and explaining it all so well.
Absolutely.
And then for something completely different, Emily Ryle, who's a category theorist. She does the most amazing, incredibly deep, complicated pure math work, and still writes like great textbooks. Her Introduction to Category Theory is one that I would recommend for anyone. Category Theory in Context is just a great introduction to the subject, and it's just so approachable. And she's just amazing in general. So there's 4 people off the top of my head.
Okay, that's great. I'm gonna look. Well, I know Vincent, and I'll look into the other. I'll look into the other ones. All right, I think we're ready for the final or almost final question. So, well, yeah, you described yourself, I think, as a mathematician turned data science. But I'll phrase the question: what is a career in research taught you about life?
Well, one of the things I've learned talking to domain experts on their data is that there's a whole lot that I know almost nothing about. In fact, almost everything I know almost nothing about. And that's always worth keeping in mind, is how many other different things there are out there and how little you know. So research also taught me I definitely don't have all the answers, and that's okay. You've got to learn to live with that. You don't have all the answers, but maybe you can get there. And that you just need to be patient with problems. Sometimes these things just need to sit in the back of your brain for a long time, and then eventually, I don't know what subconscious process works back there, but eventually answers do come out. So just be patient.
I like that. Yeah. I think that's research has always led me not to answers, but to just more questions. And then, I can definitely relate to the second one. Sometimes problems, not that they solve themselves, but like once you stop thinking about what the solution is going to be, or you do something else, go exercise, or like, those shower ideas where you're not thinking about anything else, that's when you get, some of your best ideas. That's great. That's really good advice. It's definitely how you could apply some of the thinking of research to dealing with the uncertainty of life. And how little we know, like how little we know, right? The only thing I know is that I know nothing. Leland, this has been such a pleasure. I've really enjoyed talking about all of these things. Thanks for going through topic modeling, all of your amazing libraries. If there are listeners out there that want to learn more about you or any of the work that you're doing, where would you direct them?
Probably GitHub, I guess, has most of the projects. I try and make everything open source as much as possible. So L McInnes on GitHub, but also the Tutte Institute GitHub page. You can find a bunch of our projects there as well. You can also find me, I think, on Twitter and Blue Sky. Search for my name. I guess I have a sufficiently novel name that hopefully you'll find me. And my email address is out there, so you can always reach out there or on LinkedIn or whatever if you want to get in touch.
Very cool. Yeah, and for anyone that is not familiar with these libraries, you should definitely check them out. UMAP, HDBSCAN, and DataMapPlot, and I'm sure soon enough there'll be some more exciting ones or extensions to these. Leland, thank you so much for the work that you do. Thank you so much for the time and letting me pick your brain for a little while.
Thank you.
Appreciate it. On this episode of Learning from Machine Learning, I had the privilege of speaking with Leland McInnes, the creator of a suite of data science tools including UMAP, HDBSCAN, and DataMapPlot. His work has significantly impacted the field, particularly in the realm of unsupervised learning. What sets Leland apart is his unique approach to data science problems, deeply rooted in his background in pure mathematics, particularly algebraic topology. He views data through a geometric lens, seeking to understand its underlying structure. This led him to develop UMAP, an essential dimensionality reduction technique that excels at capturing both local and global structure of datasets. We also discussed HDBSCAN, a robust clustering algorithm known for its ability to handle noise and variable densities within datasets, making it highly effective for real-world applications. Beyond his technical contributions, Leland shared valuable insights for aspiring data scientists and researchers. He stressed the importance of not just blindly following hype, but instead pursuing passions. He discussed the importance of embracing interdisciplinary thinking, and how many of his breakthroughs came from connections between seemingly disparate areas of study. Leland highlighted the importance of decomposing black boxes, encouraging a deeper understanding of how algorithms work, rather than treating them as impenetrable mysteries. By breaking down complex algorithms into their fundamental components, data scientists gain knowledge and flexibility to adapt them to new problems and data types. This approach promotes transparency and empowers data scientists to be more than just algorithm users. They become algorithm creators and innovators. Leland's journey underscores the power of curiosity, the importance of interdisciplinary thinking, and the value of understanding the tools we use. By embracing these principles, we can unlock the true potential of data science and continue to push the boundaries of what's possible. Thank you for listening, and be sure to subscribe and share with a friend or colleague. Until next time, keep on learning.